And now we are going to introduce automaton. In Explorer, we are more familiar term comes out automata. Okay, automaton is a multiple. Automata is a multiple of automaton, and these are traditionally created automaton. Okay. So you know that there are many exhibitions now these days. Previously, this is a kind of interesting working mechanism with latches and gears and cams and all those mechanical elements in it. And then we give some energy like hand wires or some motors. And then if we provide some enough energy, then it works like this or like that and so forth. Okay? And this automaton is kind of interesting because then we don't have to do anything about it. We just provide them a triggering event or enough energy to be activated. And then what it does is that something funny, something that we can watch as a toy and so forth. And then those were called as an automaton. And now what do we have? We have some drones we have some the manipulating robotic arms and so forth. And then this has a very sophisticated mechanism to do some kind of activation like this. And if it is doing nothing unless we give some instructions in it, then it's not working like a real automaton. However, we can program some of those scripts in those drones and robots, then it will start work like these types of automaton. So now these days, we still have automaton in many around ourselves. So automaton is a self-operating machine. So self-operation is kind of key term here, and sometimes used to describe a robot, or specifically an autonomous robot. Okay. So if it is always waiting for our instruction sets and always require our intervention in it to do some actions with that robot, then it's not an autonomous robot. However, if it is programmable, and if we can provide some programs to do some autonomous actions, a sequence of actions by that robot, then we can call it an autonomous robot. Okay, and it's contained like closed self-operating mechanism. What we already have here is a energy providing or some triggering events. And afterwards, human does not require those kind of the operations. So it's self-contained. Okay. So here, self-operating is important. However, for more important words is the contained machine. Okay. Traditionally, it has been utilized. It had utilized the mechanical mechanism. So it has been a continuous system and continuous state. However, we can create these types of automaton as a small software, and we make it as an object, and it has all those states and the behavior routines in it. And our invocation will start rolling of its movement like the A-queen's problem of those queens. In that case, in computer system, it will be discrete system and it's discrete state. We have to provide some triggering event from outside, and that automaton will generate some events to the outside world. Okay, so this is one single automaton. Looks very mechanically complex. However, we kind of understand with some our X-ray machine, X-ray vision, that how it is being operating inside of those gears. Our further focus, we are going to focus further on how to make this automaton multiple so that we can create it as a set of automaton interacting with each other, so eventually can be called automata. So I introduced automaton in the previous slide, and we were asking that how to make this automaton meaningfully multiple, and so that we can how to create the automata. So the problem is the interaction in between these automatons. Okay, if some events comes out, how to feed that event to some other automaton, and how to create that event's output to the other automaton, and so forth. And to do that, we require a certain structure of how they are working together in terms of a structure of an automaton. So one of the examples is the cell automata. It's a discrete model studied in many of those mathematics, physics, complexity science, theoretic biology, and computer science, and so forth. So cell automata has been utilized in many different places. It's a microstructure model. Okay, it has its cell structure, cell as an automaton, and the cell is being connected to each other. How? As a grid of cells. Okay, and that grid is a layout scheme of that automata, which is a set of automaton. Okay, so automaton is connected in like a grid way, like the two-dimensional grid or three-dimensional grid. We can do many different variations, and each of those cells will be an automaton. And this cell automata has been studied by many prominent researchers, and one of them was John von Neumann. Of course, I have to mention him, right? So this John von Neumann is one of the inventors in early days of cell automata. At the time, it has been called as self-replicating system. And here we have two different aspects on the cell automata: cell itself and its connection structure, which is referred as a grid here. And why do we make this cell connected to each other? Because a cell will change its states based upon its own state. Itself will create a different variations, different state transitions, and also its its neighbor states will create invoke the same changes, similar changes to that cell's state. So it means that, so if we say that we have a certain cell here, and that cell will transit to the other state based upon by itself, also coming from the other linked, connected cell's state. And also it has its own transition rules, okay? And many times a single transition rule is shared by all the cells. So even though these are cell automata and automaton are different each other in terms of their state, having said that, their transition structures can be shared across these many cells, okay? And states might be binary, continuous, a set of vectors, and so forth. And here, this is one simple creation of the cell automata, and the dots are moving, okay? Black boxes are moving across this white plane. And then somehow it is changing. Each of these cell pixel is changing its state based upon the cell's its own state color and also by neighboring color. So here a pixel is a cell and an automaton, And binary states are the pixel state, a cell state, and automaton state. And what's the connection of these? The connection of these are two-dimensional grid. Two-dimensional grid, and of course we can define the two-dimensional grid here. So now we have some ideas, concepts of that serial automata, and let's play some, let's do some kind of simple examples on these types of serial automata. And we are going to do some one-dimensional serial automata simulation by our hands. Okay? So here one-dimensional means that so we have one dimension of automaton, and automaton is each of the cells and its neighborhood are defined through one-dimensional way, so that connected to each other as a line. Okay, and let's see how that state changes over time given the initial states of 0, 0, 0, 0, 0, 0, and 1 and 0, 0, 0. If it were given a certain transition rule like this. Okay, so here a cell is positioned at the center value. Okay, here, so that 1 means it is the center, by itself, it has a 1. It has that one value, or 0 value, and left hand side, right hand side will have 1 value and 1 value, or 1 value and 0 value, and 1 value and 1 value. And its resulting state change is going to be only affecting itself. So its own state was 1, and these two aspects, two values are coming from the neighboring state. Neighboring automaton state, and its own what it can control as a cell is itself. Okay, so that its center value can change, transition to 0. State value will transition to 1 to 0, or 0 to 0, and 0 to 1, and so forth. So this is a transition rule of itself. Okay, so transition rule of state itself, and state before and state after, and then its next time state. Then now we can operate. Now we can operate by the hands. All right? How? Let's do some iterations. So first iteration is that, okay, so here let's say 0, 0, 0, and it will create 0, okay, so 0, right? And 0, 0, 0 will create 0. So here, 0, 0, 0 will create here 0. And now it's something new. 0, 0, 1, 0, 0, 1 is here, and it will create what? 1 here, right? And 0, 1, 0, where is it? 0, 1, 0 here will create 1 here, right? 1, 0, 0, 1, 0, 0, where is it? Yeah, here will create 1, and 0, 0, 0, 0, 0, 0 is 0, and 0 is here, okay? So this is how it has been progressed over a one single time step. Okay, next time step transition. And then now the states are a little bit different. And let's do the iteration one more time. Okay, and all the same story. And here 0, 0, 1. 0, 0, 1 was 1, so here 1. And 0, 1, 1 was what? 1. And 0, 1, 1 was 1. And 1, 1, 1 was what? 1, 1, 1 was 0, so here 0, and 1, 1, 0 is 0, okay? 1, 0, 0 is what? 1, and so forth. Is it interesting? Is it meaningful? Does it make any sense? So, if we but however, at this moment, now up to this moment, you've learned how to do a one-dimensional serial automata transition, and now you can do it by yourself. Let's do the next transition by your hands. Okay, I will write. Okay, you did that. Did it match this pattern? And then we can do it one more time, and somehow it makes certain pattern looks interesting. Does it mean anything? So that's the main question of studying cell automata. And we can do further iterations, and one cell, this one triggering event will affect other cells, and it creates certain kind of complex patterns. But what does it mean? What does this pattern mean? That is our main question as a modeling simulation. Someone who studies modeling and simulation. Okay, that's the main question. What's the real purpose of this cell automata progress?